So after we have taken actually the experimental study, the theoretical study, the derivation of the differential equation, and then we have found tau using the solution, then we verified the solution, then we have used other forms of the solution, and we found A, B, and lambda. Now I'm gonna begin with or continue with the note. Tau is equal to RC. So tau is in seconds, and R is in ohms, and the capacitance is in farad. Such that, so if we have here second is equal to ohms times farad. Is this true? This implies the second is equal, ohms is actually the volt over ampere, because if we use the wizard triangle, U is equal to Ri, so R is V over I, U over I, or voltage over amperes, times the farad is actually coulomb over the voltage. Why? Using the wizard triangle as well. So the capacitance is equal to the charge with respect to the voltage. So Q over U. So the coulomb over the voltage. So the voltage with the voltage will cancel out. So it is coulomb over ampere. However, whenever we want to speak about coulomb, it's actually ampere times second. Ampere times second, a coulomb. So Q is equal to I over T, or it's vice versa. So a coulomb is ampere times second, so ampere over ampere will cancel out, it will be in second. Now we're going to continue the fifth part. The fifth part, we're going to use the solution. However, using the solution, U of C of T, which is E into 1 minus exponential minus T over tau. That's the classical form, but there are another form, and we have taken it. Actually, we're going to draw. So here we want to represent graphically U of C of T. Represent graphically, okay, we're going to make some analysis for this graph. So let's begin. For T is 0. For T is equal to 0, what's going to happen? This implies, so U of C at 0 is equal E into 1 minus T is 0. 0 over anything, a number, is 0. E to the 0 is 1. 1 minus 1 is 0. 0 times E is 0. For T is equal to tau, what happens? U of C of 1 tau is equal E into 1 minus tau over tau, so it is E minus 1. So it's equal to E into 1 minus 1 over E. And some calculations will lead us to 0.63. So this implies that U of C at 1 tau. So after one period of tau, which is the time duration for charging a capacitor, how much percentage? It is 63%. So it is 63% of the maximum voltage. So 63% of the maximum voltage. We're gonna draw it there. For T is equal to 3 tau, 4 tau, 5 tau. So I'm gonna put like 3 dots here. At 5 tau, U of C at 5 tau, what's gonna happen? The same idea is equal E into 1 minus 1 over E to the 5. So it's actually around 99.3. So if you calculate this 1 minus 1 over E to the 5 tau is equal E times 99.3% of E. So 99.3% of E, this means that it's not gonna reach exactly the maximum value, but it's gonna reach almost the maximum value. This means that there is a certain asymptote, and it is a horizontal asymptote we're gonna draw. So we have here the figure and then we're gonna draw the other one. That's the first one. Gonna draw the t-axis. So that's the t-axis in seconds, and that's u of c of t in volts. And we're gonna reach actually a maximum value E. So E is the maximum value. So that's actually gonna be the asymptote we're gonna draw here. That's E actually. And that's called the asymptote. So let's begin plotting the points. At t0 equals 0, u of c is 0. So we're going to take some scale, 1, 2, 3, 4, 5. So if we're going to calculate 5 times 0.63, or 1, 2, 3, 4, 5, so let this be 10, let's say. Let E be 10. Okay, so this is gonna be 63, so 6.3, 2, 4, so that's 2, 4, 6, 8, 10, a scale of 2. So it's gonna be 6.3, so 6.5, this is 7, this is 6.5. So at this 6.5, we have 1 tau. So for every 1 tau, 63% or 6.3 here in this case, 6.3%, 6.3 voltage actually, 63% because it is 10. And 2 tau, 1 tau, 2 tau, 3 tau, 4 tau, 5 tau, that's 3 tau, that's 5 tau, 4 tau, 2 tau. What's going to happen? We're going to have 2 phases such that each phase is going to be identified. So we have here, it's going to go this way. So this is the transient phase. And then from beginning from t equals 5 tau, we're going to have the steady state. Steady state or permanent state. Or permanent state. Okay? And that's actually the asymptote. It's going to continue this way. Okay? So this, you see this? This is not going to be 100%. This is going to be 99.3%. It's going to approach. It's going to tend to go very close to the asymptote, but it's not going to hit it. In the transient phase, from 0 here, from 0, it's going to go to almost 5 tau, is the transient phase. While it is charging. So while from 0 to 5 tau, the capacitor is charging. Okay? And at 5 tau, the capacitor is fully charged. Okay? Fully charged capacitor. Now we're going to study something in the curve. If we elongate or extrapolate this to hit a point on the asymptote, let us call it F. And then here, point A. So AF, how much is AF? If we project it, we see that AF is tau. So from the graph, we can see something which is very important, and we're going to study. What is it? If we take the tangent to the curve at t0 equals 0, here, this tangent is actually the slope, which is duc over dt at t0 is 0. At t0 is 0, we have e minus 0 over tau minus 0. So it is actually e over tau, which is a positive constant or positive slope. So that's actually the slope or the tangent to the curve. That's the graphically. However, if we want to use the equation, the differential equation that we have already derived. What is the differential equation? The differential equation, duc over dt plus 1 over rc times u of c is equal e over rc. At the maximum voltage of the capacitor, at the maximum voltage of the capacitor, we know that something which is very important, which is called duc over dt plus the other stuff that we know, the derivative of it. So from the differential equation, we have the solution. Let me write the solution directly, because there is no space here. Let me write directly the derivative of u of c. So duc over dt from the solution, we know that the solution is this one. So the solution of this one is e into derivative of 1 is 0 minus exponential of minus t over tau times the derivative of the exponent, which is minus 1 over tau. So minus times minus is plus, so this is equal to e over tau times the exponential of minus t over tau. However, when t goes from 5 tau onwards, this means that t goes to infinity. If t goes to infinity, what does this mean? E to the infinity, to the minus infinity, is e to the minus infinity. 1 over infinity is 0. We don't want this. What do we want? We want it at tau. At 1 tau. If t is tau, what does this mean? It's minus tau over tau, so it will be 63%. If it's 2 tau, it will be like 86 point something, 93 point something, etc. We need to actually determine when is this 0. At t0 equal to 0, we're going to take the derivative. So the derivative at t0 equal to 0. It's not at tau, it's not at 5 tau, it's not at infinity. It's actually at t0 equals 0. For t0 is 0, 0 over anything, number of course, is 0. So e to the 0 is actually 1. And this will lead us to the same conclusion that we have done graphically, which is e over tau. And algebraically, using that equation, it is e over tau as well. And we know tau, that tau is RC. That's actually the representation of the charging of a capacitor. So that's gonna be called charging of a capacitor in its transient phase and steady state. I'm gonna revise in 2 minutes. What we have done here, that we have proven that tau is in seconds using some units. And then we have used so the solution of the differential equation. We have put some particular values, 0 tau and then 5 tau, so that we got at 1 tau of duration, we will get 6.3 volts. So for 1 tau, for the first tau, we will get 63% of the maximum voltage, and then we will continue a transient phase until we reach the steady state from 5 tau onwards to infinity, asymptotically very close to the asymptote, which is the maximum voltage of the generator. And then we want to prove that the slope at t0 equals 0 is z over tau, which is positive, and we have proven it actually from the derivative of the differential equation at t0 is 0, and we found that they are convenient, they are in harmony with each other. And enjoy physics.